Let's talk about phase changes. We've talked before about the three main phases, which are solids, liquids, and gases for any particular substance. And when you go between the different phases, we have names for those processes. And we said from going from a solid to a liquid is melting. Going from a liquid to a gas is boiling or vaporization. And going the opposite way, if you're going from a gas down to a liquid, that is condensing or condensation. And going from a liquid to a solid is freezing. Okay, but you can also sometimes go directly from a solid to a gas without passing through the liquid phase, and that is known as sublimation, or the opposite case is known as deposition. All right, so we can look down, and we can also remember that not only is enthalpy increasing as you go from solid to liquid to gas, but also entropy is increasing. Okay, so enthalpy, which is heat, and entropy, which is disorder, both increase going up in that diagram. All right, and then looking at specific, those specific terms, melting is solid to liquid, vaporizing is liquid to gas, subliming is solid directly to gas. And then the opposite cases, condensing is when a liquid forms from a gas, freezing is when you go from a liquid to a solid phase, and deposition is gas to solid. And so these all occur for every type of substance. And for these top three, we have a positive change in enthalpy, and for the bottom three, and entropy as well. And for the bottom three, we have a negative change. And there were special names for these processes. Melting is the delta H of fusion. Vaporizing has the delta H of vaporization associated with it. And for subliming, it's delta H of sublimation. So of course the opposite processes will have the same value of enthalpy change, but the opposite sign. So condensing will be the negative of the delta H of vaporization. Freezing will be negative delta H of fusion. And deposition will be negative the delta H of sublimation. All right, now let's look at what we call a heating curve. And we're going to do this specifically for water, but it can be done for other substances as well. So a heating curve is where you have on the x-axis heat added, okay, which is Q, and on the y-axis is temperature. So as you take a substance from a solid and add heat, it will get warmer and warmer and warmer. So we go up. So as you add heat to it, by putting a flame under it or whatever you do, as you add heat, it will get warmer and warmer. Okay, that makes sense. But at some point, you hit the melting point, and then the temperature, as you continue to add heat, the temperature does not go up. Okay, the reason for that is instead of the heat going to increasing the temperature of the substance, it's going into changing the phase of the substance. All right, and then you have another portion of the graph where once you get to the liquid, once everything's been converted to the liquid, then you also, as you add heat, your temperature will rise. And until you get to the boiling point, and then again the temperature will be steady even though you're adding heat until you are done getting everything to the gas phase. And so this third increase in temperature occurs when you're in the gas phase. Okay, so in those places, those phases, gas, liquid, and solid, you add heat the whole way, but you're adding heat and that goes into warming the substance. So I'm going to say added heat goes to warming. And which basically means that you're adding kinetic energy to the substance by warming. All right, but the flat portions are where you are doing phase changes. And if we're doing this for 1 mole, then we can say that amount of heat you add between a solid and a liquid is exactly that delta H of fusion. Okay, so this energy, this heat amount added is the delta H of fusion because it's for 1 mole. And again, up at boiling, the amount of heat that is added, if it's 1 mole of the substance, is going to be the delta H of vaporization. So that amount of heat is the delta H of vaporization. All right, and while you're doing those portions of the graph, the added heat is not going to warming, the temperature is not changing. In these cases, the added heat goes to breaking bonds. And those bonds are the intermolecular forces between the molecules. So it goes to breaking intermolecular forces, and that is going to changing the potential energy. Bonds are potential energy. All right. Since in this case we're talking about water, we can also say where these phase changes are occurring. We can say that the temperature where this flat portion occurs for water is 0 degrees, and the temperature where this flat portion occurs is going to be 100 degrees C. So we know those two temperatures. All right, so when we are within a phase, in other words, we have an S, an L, or a G within a phase, we can say that the heat amount given, since it directly goes to a change in temperature, can be given by Cm, or I'm writing it backwards, but Cm delta T. So we can say that the Q for the solid is equal to C solid water times the mass of water times delta T. And the Q for the liquid portion, whoops, too far. The Q for the liquid portion is similarly the heat capacity for the liquid form of water times the mass times delta T, and the Q for the gas will be the heat capacity of the gaseous water times M times delta T. Now the heat capacity for liquid water we already know is 4.184 joules per gram Kelvin. We've used that number many times. All right, so they each have their own heat amount that you can calculate for their phase, because this is water. And then the other heats, so within the phases, we can get heat from the delta T, and between phases we can get the heat based on the heat of vaporization and the heat of fusion and the number of moles that are present. All right, so now we'll look at a sample problem for you to use your understanding to answer. So consider the heating curve shown for 1 mole of a pure substance, not necessarily water. In the arbitrary units displayed, what is the value of the enthalpy of fusion? So figure that one out. Again, we can look at the heating curve. This may not be water, but we can say that the lowest one is a solid, the middle one's a liquid, the highest one is a gas. And we can look at actual numbers of heat added, although they're arbitrary units. And if it's for 1 mole, then this place here would be delta H of fusion. That's how much heat was added. And this place here would be the delta H of vaporization. So the enthalpy of fusion for this case would be this distance, which is 150 minus 50. So delta H fusion equals 150 minus 50, or 100 units.